today. We're going to start recording. We were here. Oh, if you wouldn't mind shoving that, just to hold that big stack right in front of you, just forward. Yeah, just push forward. Yeah, you don't need that. And then on top of the filing cabinet next to Zaid, you're going to see it's going to look like this on the front, acceleration due to gravity. And then you're going to flip to this page in the middle, and you'll be all set.
Can you do a little bit of a summary of this though?
Oh yeah, we got a bunch of examples coming here, so it'll be okay. It'll be okay. Okay, so projectile motion. I always start, especially when there's been some time, start with a little bit of a recap here. Recall, a projectile is anything that flies through the air where gravity is the only thing acting on the object. So we ignore things like lift due to wings, so like a glider wouldn't count. We ignore anything that has an engine, like a cruise missile, for example, would not be considered a projectile by this definition, because the cruise missile actually has something propelling it forward. It's not going to be following the same path. Also, I mean, they're also constantly course correcting, and so there's a whole bunch of wild going on there. A projectile would be like old school. Think like a spear, or a bow and arrow, or even just a bullet is a pretty good example of a projectile because they don't have wings. They're not generating lift. The spin just gives them some stability as they fly through the air. It doesn't actually keep them up at all. So anything that does one of or behaves like that in the air is considered a projectile. And for a projectile, I tried to establish last week that this was true. Not last week. Monday? What day is it today? Monday I did this. Yes, I'm going to actually. I'm going to show it to you. I didn't put it up because I'm going to show you right now.
Yay!
So they hit the same. For objects that are thrown sideways versus just dropped. And I tried to argue this with a hockey ball and a baseball rolling off of the desk at the back, and I thought it did a decent job. It doesn't matter what kind of horizontal velocity you give these objects, because ultimately we're ignoring anything that might give them lift. Like there's no wings on a baseball, for example. It doesn't matter how fast the thing's going horizontally. These two objects are going to hit the ground at the same time, just not beside each other. And they're going to hit the ground at the same time because this object and this object have the same vertical acceleration. They're both being accelerated downwards at negative 9.8 meters per second squared. It doesn't matter that this one has been given a sideways velocity as well, because that sideways velocity is just going to give it some sort of trajectory that'll land it over here. These two objects will still hit at the same time. Yes, Manuel?
In the experiment, is the one that falls straight down shot or just dropped?
It's dropped from the same height that the one that was shot. I'll show you. I'm going to load it up right now. Which makes way more sense.
I thought both of them were shot.
Well, they can't both be shot. Because they both have to have the same initial vertical velocity, in this case 0. So one's going to be shot sideways, and the other one's just going to be dropped vertically from the same height. Which is, it's going to be interesting how they set this thing up. So I want Mythbusters bullet drop. Here we go. Oh, and I need my speakers. Thank you. Okay, there we go. Where are you? You're right there. Okay, cool. Do this one. No, I don't want this one. You know what? I'll just go to YouTube. Let's take a look at what these things will practically look like. So flip the page to the blank. I got a couple blanks here, and we're going to do a bunch of examples. Do this one's first. Okay, so our first example is going to be this. Draw with me here. You are on the top of a building with a large ball. You are going to kick the ball to your friend on the ground. You have somehow figured out that you are capable of kicking such that you're going to give the ball a velocity of 5 meters per second, perfectly horizontal. Somehow you're going to pull this off. And the question that we're going to try and find is, where should your friends stand so that that ball lands at their feet? So I'm hoping I have sufficiently convinced you that we can separate out what's happening to this object vertically and horizontally. Yes? Have I convinced us of this? Okay. And so that's how we're going to set up the equation. Sorry, no, I lied. Before we even talk about equations, that's how we're going to set up our data. We're going to talk about what's happening horizontally, and we're going to talk about what's happening vertically. As far as like the mathematics go, assuming that we're dealing with just a regular Cartesian plane, horizontally is typically considered to be an x variable, vertically is typically considered to be y, but we're going to use those interchangeably. So when I talk about x variables, we'll talk about horizontal. We're talking about y variables, we'll talk about vertical. So what do we know for our object in both the horizontal plane and the vertical plane? Oh, and I haven't told you how tall the building is. This is a 50-meter building. So 5-story building. What do we know?
The vertical distance is 50 meters.
So the displacement vertically that the ball is going to travel, it's not 50.
Oh, it's minus 50?
Yeah, it's going to be negative 50. Why is it negative?
Because, like, if you consider the low level is positive, so negative.
We're going to call that direction positive, and we're going to call that direction positive. Right, so down is going to be negative. And the ball, it's not about the distance the ball is falling, it's about the distance and the direction that the ball is going. So the ball is going to go 50 meters down. That's going to give us a negative displacement. What else do we know? Manuel, is that a hand?
Yeah, we know the horizontal velocity.
The horizontal initial velocity, or just the horizontal velocity? VIX is 5 meters per second. What else do we know? The vertical initial velocity, so VIY, is going to be 0. We know the vertical acceleration is negative 9.8 meters per second squared. Cool. Is there anything else we know? There's one rather important piece of information that I want to include here.
Something related to the range or
That's AY, here's AX. What is AX? Does my object accelerate horizontally? No. After it's been kicked, it doesn't accelerate horizontally. So my acceleration in that plane is going to be 0. there's one more, actually there's two more things we could write here. We want to know what the range is, so we got to talk about d. The distance, so that's y. D in the x direction is what we're looking for. And there's one more concept that we can talk about here. Time. What's going to be true for time? So if I list time here in the y direction, and I list time here in the x direction, what's going to be true about those two times?
Yeah, it's the same.
They have to be the same.
So if you solve it like directly, you can like solve the distance factor.
Right. That's exactly what we're going to do, Luis. So we've split up everything we know about our object horizontally and everything we know about our object vertically, and we were able to connect them with the fact that time is independent of space. It doesn't matter if you're going vertically or horizontally, or both vertically and horizontally. Time is going to pass the same for you in both directions, which is important, but ultimately you might find that to be trivial. So what we're going to do here is actually what Luis just said. We're going to figure out what the time is using our information vertically, and that's going to give us what our range is going to be over here. So Luis, what formula can I use to figure out how long it takes my object to fall? Okay.
D equals VIT plus 1 plus 2 times AT squared.
Cool. So the beauty of this equation with this set of information is what? Yeah, VIT is 0, so that's gone. And so now I can just fill in the rest of it. D is going to be negative 50. That's going to equal 1/2 negative 9.8 t squared. So what's t? It's going to be negative 50 equals negative 4.9 t squared. So negative 50 divided by negative 4.9 and then square rooted is going to give us what value? Sorry? 3.19. Okay. And because time is the same vertically and horizontally, like the time it takes for it to drop is going to be the same amount of time it takes for it to get over here, we can say that, well, this time is also going to be equal to 3.19 seconds. And then what equation am I going to use to figure out the horizontal displacement of our object? I can use the same one, except in this case, so D equals VIT plus 1/2 AT squared. The beauty here is that what goes away?
The acceleration.
Yeah, the acceleration is 0, so this whole term is gone. So then our distance, or rather our displacement in the x direction is just going to be its initial velocity, 5, times 3.19 seconds. What's the range of our object? 15.95 meters. There it is. Cool. Easy, yeah? Relatively. Questions, comments, concerns about any of this? Okay, cool. Let's do another one. Another kind of example for a problem like this. You're only going to be on top of a building again. Here's you on top of a building with an object that you're going to launch the horizontal velocity of 8 meters per second. you're going to measure that the distance this ball travels horizontally is 23 meters. How tall is the building? That's what we want to find out. So for any problem like this, we set it up exactly the same way. When you've got an object moving in 2 dimensions, split up those dimensions because they are going to be independent of each other but related usually by a single variable. So I'm going to break up this projectile into my horizontal and vertical components. And now let's fill this in. What do we know? Hold on. So we had AX equals 0. Cool. Luis, you said VIX is going to be 8 meters per second. VIY is going to be 0. AY is going to be negative 9.81 or negative 9.8. You can use those values interchangeably. I mean, they're going to change it to a couple decimal places, but ultimately not that big a deal. What else do we know? We know that the times are going to be equal. And we know the horizontal distance is 23 meters. Cool. Anyone want to take a guess at how we would approach this?
We discover the time of the x-intercept, and after we're going to plug in the y formula and discover the displacement.
Okay. So Luis has said we're going to use our horizontal information this time to figure out what the time is, because that's where I've got the bulk of my information. So I've got a dx, a vix, and I'm looking for t. Because there's no acceleration, I can jump straight to this, d equals vt. But I want to find the time. So I could, if I wanted to at this point, I could just isolate for t. Divide by v, it's going to cancel. So I'm going to get t equals d over v. D is 23, and my velocity is 8, which is going to give me a time of what? Exactly 2.9? So let's go 2.88. Because you gave me 2 decimal places before, let's keep it to just 2 decimal places. And then, as Luis already said, we're going to take the time here now, because we know they're equal horizontally and vertically, we're going to take this and we're going to plug it into our information over here. Which, I'm looking for dy, which kinematic equation are we going to use here? Is the same as d equals vit plus half at squared. This is gone because viy is 0. The dy is what we're looking for. We're going to get 1/2 negative 9.8 times 2.88 squared. What is dy? Negative 40 point. Okay, so what does that value actually represent? The displacement of our ball, yeah. So it went down 40.64 meters. So then what's the height of our building? 40.64 meters. Cool. Comments, questions, concerns? one more. Blank page here. We've got a table, and I tell you the table is 1 meter tall. From this position here, I have a dart gun. The dart gun, we'll say from the table to right there on the dart gun is 0.1 meters. We pull the trigger on the dart gun. And we can measure on the ground that our dart has gone 6 meters. We also measured with a stopwatch that the time it took to do this was 0.6 seconds. What's VI?
Oh, so it's divided horizontally and the vertical thing?
Okay, so let's divide it up horizontally and vertically because this is a projectile. That's how we approach this thing. A little bit here.
The vertical displacement is minus 1.1 meters. The horizontal displacement is 6 meters. The time is the same in both. The acceleration of y is minus 9.8 meters per second, and the acceleration in m is 0. And yeah, now you can do the
There's one more important piece of information that we ought to include here, Luis. Okay. Sorry? Vy is?
oh, y 0.
0. Okay, so this is the situation. Okay? This value here was measured. So assuming that that's true, what's the velocity of my gun? The initial velocity of the dart. Do I need any of this information over here? Okay.
You can just solve the formula with the two pieces of information you have, and that's it.
I could just solve it with the two pieces of information I have. Sure. Okay. So I've got V x is just going to be d over t, right? So we can find that we know that the horizontal distance was 6, and we know that that took 0.6 seconds. So based on what we've got here, Vx is going to be 10 meters per second.
To be honest, you can just figure it out this, the time is 0.6 and 6 meters, so you can divide 6 meters by 0.6.
Right, yeah. But I told you this was measured. Do we have a way of figuring out if that's accurate? Well, we know what the acceleration due to gravity is. We know we didn't shoot the dart up. And we know that the dart was being dropped from a height of 1.1 meters. So we could work it backwards. Okay, so let's see how good this measured value for time actually is. Yeah, Naya. Sure. Let's see how good this measured value for time is. To do that, we're going to figure out what the time should have been using this information here. So to do that, we're going to use dy equals VIYT plus 1/2 AYT squared. Beauty here is that VIY is 0. And I know that dy, we measured dy, the distance from the floor to the gun. Why are we going to the middle of the gun, by the way? Why did Luis want to add that 0.1 meters?
The total displacement is going to add the height of the gun and the height of the table, so the gun is like a little bit up.
Yeah, because the dart's not being dropped off the table, it's being shot out of the barrel of the gun, and the barrel of the gun's a little higher. Good. So I've got a dy here of negative 1.1. That's going to equal 1/2 negative 9.8 t squared. What should that time have been? Sorry? Did someone verify that value? Someone else get 0.45? I feel like it should be bigger than that. 1.1 divided by 9.8 square root. No. Square root answer. Okay, 0.47 is what I got. So we're out by our theoretical time versus our measured time is points. One was 0.47, one was 0.6. A difference of yeah, 13 milliseconds. Is that reasonable?
Yeah, I think that's, I don't know, it's 10% or, yeah.
I want you all to grab your phones out and open the stopwatch. And on your stopwatch, I want you to hit start and stop as fast as you can. Oh, I missed it. Okay. What time is we getting here? 0.16. You got 0.1. I got 0.18. Tristan, I see, got 0.13. So this length of time is my reaction time is effectively what I'm measuring here. The speed at which I can start and stop my stopwatch. So is a difference of 0.13 seconds reasonable? Can that be explained by error? No, but think about what we just did here. Can I explain the difference between the 0.6 seconds and the 0.47 seconds? Yeah. I can explain that by just the delay in our own ability to take a measurement. So then this is what we measured, this is what we calculated. How fast should the dart actually be traveling? Let's do the Vx calculation again. We know it went 6 meters, but my theoretical time is actually 0.47 seconds. This number doesn't take into account my own inability to push stop. So how fast is the dart actually going? Are we within 10%? Well, let's look at our percent error again. Percent error is going to be theoretical, 12.77, minus our experimental,
I got 21%.
divided by 10 times 100. Luis, you got 21%?
Why did you put 10 and
Oh, sorry, 12. That should be 12. Yeah, it's 12.
I got 21.69, so 21.7.
So we have 21.7%.
Technically it's not valid, but why do you not consider because you are human, you're not person.
So if that's the only piece of error so where could we have been wrong? All of these were measured values. Do I know this is exactly where the thing hit? No. Do I know this is exactly the measured height of the gun? No. The reason I do this as the last example is because this is I know your test is on Friday for kinematics, but we're going to start on the Monday we get back from spring break doing exactly this, just to kind of finish off kinematics. This kind of stuff will be on the test. This kind of stuff is going to be the lab we do on the Monday after spring break. I'm going to bring some dart guns down, assuming they still work.
Wait, what?
We have a bunch of dart guns upstairs, and we're gonna shoot dart guns, and we're gonna figure out muzzle velocity. So this is going to be a lab after spring break. Just to finish off kinematics and to bring you guys back after 2 weeks off. To kind of get you thinking about physics again. No, this one you do not have to graph. There's no graphing for this one. I'm sorry, Luis. I know you were really disappointed by that fact. So, okay. The projectile stuff. The projectile stuff makes sense? Just this is the introduction to it? Okay, then here's what I want you to do.
In this question, check the whisper depth first.
Oh yeah, if you have the Whistler Death Quiz, please hand that in.
Why is everything so deadly in physics?
Please hand in the Whistler Death Quiz, your take-home quiz that I gave you a couple days ago. Hand that bad boy in if you did it. I know. But we still have another. We have an hour from now. So what I'm going to do right now is I'm going to assign you guys a bunch of work, and I'm going to give on projectile motion this stuff here, and I'm going to give you the review package for the chapter. I'm going to mark those Whistler quizzes and get them back to you. I mean, there's 4 questions. It'll be quick. I should be able to get that done in 20 minutes. So, Luis, you say you want to know how you did. Yeah, hand it in. I'll go through it right now as soon as you guys start working on this, and I'll get it back this block. You may. So, I want you guys to take a look at these. I do not have a lot of projectile motion problems in the review pack itself, so I'm going to assign all of these, and I want you guys to get into the habit of drawing a diagram for these things. Draw them out the way that I've drawn them out. And all of these are thrown horizontally. This is totally reasonable. Like I said, because I don't have a lot of projectile motion review, I want you to do all of this. When you're done those, the review package that I've created for you is this package right here for the front. You come grab this at any point now. So yeah, you got your on your mark, giver. If you've got the Whistler Death Quiz done, I'll take that question now. Yeah.
I did all my work for the quiz.
Yeah.
I did all my work. I think did you have to write it on the quiz?
What do you mean? Where is?
I did all my work.
Oh, it's good. Take a look.
This is
Yeah. Okay, so that was your homework from a couple days ago. Where is my...
Make the pin.